Thank you, Sanjeev. So I'm actually going to talk a little bit about this kind of personal experience of a little bit of history, not because my experience is particularly interesting, but because I think it says something about the type of thinking that people are doing in scientific community, and sometimes they change their mind in ways that are suboptimal. So it's a little bit, I always was sort of a student of epistemology or interested in epistemology. In fact, that's how I came to machine learning, by kind of stumbling on a book that was the transcription of a debate between Noam Chomsky and Jean Piaget, and there was an article in this book about the perceptron, which is sort of one of the first learning machines, and I was fascinated by the whole thing. That's when I was an undergrad. There's this big discussion at NIPS a couple of years ago that Sanjay was talking about after Ali Rahimi gave his talk, where he qualified deep learning of Alchemy. And I took exception to this. So there was a big discussion on Facebook where I posted a response to his talk, and then he commented on it, and there's something like 200 comments or something like this. So it was a very interesting discussion, actually, I thought. But I think he's confusing two things, which is alchemy and engineering. Now, admittedly, some people do engineering in ways that are indistinguishable from alchemy, but engineering science is inventing new artifacts. And there's a lot of different methodologies you can use to invent new artifacts. So let's take a few examples of artifacts, like the telescope, the steam engine, things that have really kind of revolutionized the world in some way. The electromagnet had a huge impact. The airplane, the fertilizers, things like that. The radio, certainly. And the methods for discovering those things or creating them, I mean, it's a creative act. It's not sort of the analytic scientific process that creates those artifacts. It's really a creative act. And every means are allowed as long as the result is something that's valuable. And so you use your intuition, you use your creativity, you use inspiration from all kinds of sources. You use tinkering, systematic exploration, experimentation, happenstance. A lot of things that we've discovered were discovered by accident. Antibiotics, for example, or substitute sugar. The best ones were discovered by a little bit by accident. So all of this, of course, is more efficient if we have some theoretical understanding of the sort of underlying phenomena. And perhaps what theory helps us do in the creative process is direct or creative juices, and allowing us to kind of ignore the branches that are not likely to result in something fruitful. So the theories that were built as a result of inventing those things. So very often the theory comes after the invention of the artifacts. The theory comes because people want to understand really what the artifact really does, what its limits are, how to optimize it, how to make it better. And there's some phenomenon that is discovered and we need to understand to be able to exploit it. So optics, thermodynamics for the steam engine, electromagnetics or magnetism in general, aerodynamics for airplanes, etc. Those things generally came after, or the part of this field that sort of explained the artifact, so it came after the artifact. And the methods there are very different. This is sort of part of natural science now. We have an artifact that we're studying, and there's a number of phenomena that we can observe on how this artifact behaves when we put it in a certain condition, when we modify it in certain ways. And that's what kind of builds the intuition for perhaps what the theory behind it should be. So the methods there are the methods of science, of natural science. Reproducible experiments in controlled conditions, and of course, the tools of mathematics, statistics, systematic experiments, etc. And of course, there is sort of back and forth between those two modes where one kind of supports the other. So that's sort of, I'm not, telling you anything you don't know if you're a practicing scientist and an engineer. Most of us are both. And so, as I said, the theory often follows the invention. So we can go through a few examples. The telescope was invented around early 1600s. The theory for optics developed mostly by Euler. There were theories of optics before that were completely wrong. Like, for example, in antiquity, the theory was that it was the eye that actually produced light. But that was kind of put in question relatively late, and the sort of formal theory of optics, even though lenses existed, in antiquity, putting lenses together in a complex enough way that it can be understood, didn't happen until then. So that became of sort of prime importance to really understand optics once the telescope was invented, and then the microscope and various other implements. Steam engine, actually the first steam engines go back a very long time, the 1700s. The first steam-powered boat, I think, was built in the early 17th century. Thermodynamics didn't come until about 100 years later. That's the early thermodynamics, like the Carnot cycle, for example, which is really the basic of thermodynamics, and it was designed to really understand how steam engines work. Now, that's really interesting because thermodynamics became the foundation of all of physics, essentially. That's kind of one of the most fundamental intellectual constructions of all science. And even though it was really developed for a particular purpose. The phenomenon of electromagnetism was discovered in the early 1800s, and there the theory came very quickly. And in fact, there was kind of a very quick feedback of sort of theories that explained what was going on, with Maxwell and Ampere and all these guys. Aerodynamics actually preceded the airplane, but it was really designed for sailboats. That's to kind of understand how a sail works and the notion of lift and things like this. It was Bernoulli mostly in the late 1700s. But it didn't come it was not until the invention of the airplane that the sort of theory of a wing, if you want, sort of came up, which is, slightly different it's not different from a sail, but if you want to really have a good model of it, including the turbulences at the end of the wing, etc., it's more complicated. People made compounds, of course, way before they really understood the underlying chemistry, way before the atomic theory was even proposed, which was only in the early 20th century. And then there are things that are kind of more recent, like the feedback amplifier. So the feedback amplifier, this is a very interesting example to me. If you have done any kind of electronics, you know what this is. This is basically the reason why Bell Labs was created. So Bell Labs was created in shortly after World War I with one single purpose to solve. They had one problem to solve, which was to enable transcontinental communications. At that time, you could pick up your phone and call Chicago and be more or less heard from New York, but you couldn't call San Francisco, even if you shouted. There was no amplifiers, right? And so the signal degraded, over 6,000 kilometers, and there was no signal at the other end. So how do you design amplifiers? So of course, the triode was just invented in the 20s, and people tried to figure out how you use this for amplification. But the problem with the triode is that it's a very nonlinear element, and so it doesn't produce good quality amplification. And one guy who's working at Bell Labs, a very, very young Bell Labs, which at the time was in Manhattan, took the ferry from New Jersey to go to work, and had an idea on the ferry and wrote the idea on the New York Times that he had in his hand. He was reading the New York Times, and there was kind of a margin, and he kind of wrote the basic equation of linear feedback amplifier in the margins. It's basically the idea that if you have an amplifier that sort of amplifies a signal which inverts the signal, if you take a piece of the signal and feed it back to the input, you linearize it. You linearize it, and every amplifier is based on this, essentially. So that completely solved the problem. So now Bell Labs had a problem because they were created to solve that problem. They solved it. Should we just close it off? But of course, after that, they worked on trying to make the triodes smaller, more reliable, more efficient, and then discovered the properties of those kind of weird germanium crystals, and now had to learn crystallography, for which they had to hire the first woman scientist at Bell Labs, because crystallography at the time was kind of in the periphery of physics, and so women at the time were really not doing physics, and when they were directed to areas of physics that weren't that competitive. Crystallography was one of them, but all of a sudden, they were at the center of the world, because that's what you needed to study semiconductors and invent the transistor. So that's what happened. So that that's the kind of early history of Bell Labs. And of course, closer to us, there is the computer. Here I'm kind of mentioning the programmable computers and the sort of electromechanical or electronic computers. 1941 was Konrad Zuse in Germany, who had kind of a relay-based computer, completely programmable, Turing complete, and then of course the ENIAC in the US. But computer science didn't become a field until the 1950s. I think the first degree in computer science was in the UK in 1953 or something, and the first in the US was in 1962. So that, it took a while before it kind of established itself as a science. And of course, very early on there was the telecommunication, telecommunication through teletypes, which are basically remote, typing machines. And but information theory, also coming from Bell Labs, didn't come until after World War II. There was quite a bit of work on this by various people, actually, not just Shannon, before that. Okay, so that's kind of, the magical objects of our modern world, have been invented before they were completely understood, essentially. And this is a little contrary to kind of the fairy tale that we tell young students or school children, at least in France, where we have a tendency of being a little formal in terms of mathematical education, where we tell them, you do all the math, understand all the theory, and then only after that you can, kind of explain, invent things with the theory. It never works this way. Okay, so let's talk about AI, machine learning, deep learning, etc. And the inspiration there, the creative inspiration for all of deep learning today, has its roots in the 40s, where with people like Warren McCulloch and Pitts, what they discovered was they tried to kind of draw a parallel between what a neuron does, or what we knew at the time a neuron was doing, and what we knew about computation, okay, and logic. And what they realized is that a neuron is basically a threshold element, right? It computes a weighted sum of its inputs. If the weighted sum is above a threshold, it fires a spike. If it's below, it doesn't. So let's think of it as a binary element, right? And this is actually called a McCulloch-Pitts neuron. So something that computes a weighted sum and turns on if it's above a threshold, turns off if it's below the threshold. And what they showed is that behaves like a logic gate, and you can build circuits out of it and basically compute any logical functions you want. And so you can do logical reasoning with neurons. Therefore, that's how we think, all right? Then, about the same time, Donald Hebb, who's a psychologist, had this hypothesis that in the brain, learning takes place by modifying synaptic connections. And he had the intuition that perhaps what was happening is that when two neurons were firing more or less at the same time, the connection that linked them would increase in efficiency, if you want, in efficacy. Okay, so that's the notion of synaptic weight, which already McCulloch and Pitts had kind of hypothesized, and of course this was well known from physiology experiments. So that's the idea of Hebbian learning. Meanwhile, Norbert Wiener was, kind of wrote the book about cybernetics. We don't need the same thing today with the cyber prefix, but cybernetics was a field. It was kind of a field that concerns the study of complex systems that are composed of modules in interaction. And so the notion of feedback, for example, self-organization, and then, of course, the optimal filters, autopoiesis, which means, for living things, kind of maintaining your condition, your body temperature, things like that. And Norbert Wiener actually built this little robot here, which had like light sensors, and this thing is like an insect. It kind of drives itself towards the light. Okay, it's very simple to build. You can build this in a weekend if you want. Completely analog, of course. No computers. There was no head. And that's okay. So that's the perceptron. This is Frank Rosenblatt, and the perceptron was really kind of the first learning machine that was implemented with kind of an algorithm that seemed to work and do something useful. Really, I think what Rosenblatt invented in this context is the concept of supervised learning, really, or pattern recognition through supervised learning. And so the perceptron was not a program on a computer. It was an actual analog computer where the first layer was a bunch of randomly connected neurons connected to a retina, which we don't see here. And then the second layer was a bunch of neurons with adjustable weights. And so what you see here is a row of such weights. Each little thing here is one of those weights. It's actually a potentiometer with an electric motor on it. Okay, so when you want to train the machine, you show an image to the photo detector. There's an array of photo cells. And then you press a button for class 1 or another button for class 2, and all the motors go quick. So how long you press basically determines the learning rate. So this concept of supervised learning is kind of what Sanjay was presenting earlier. You have you want to train a machine to distinguish images of cars from images of airplanes, and your machine is basically a parameterized function with adjustable knobs. And you show an image of a car. If the machine says car, you do nothing. If it doesn't say car, then you tweak the knobs so that the output gets closer to the one you want. Okay? And then you do that with an image of an airplane, and you keep repeating this with thousands of examples. And of course, in a real neural net, you may have hundreds of millions of those knobs. And you can view this as the process of minimizing some objective function, which is the average discrepancy between the output you want and the output you get out of the machine. Okay, so that's supervised learning. So the work on the perceptron led to a kind of a standard model of pattern recognition that has survived until today, but it's less prominent now in the last 5 years since the emergence of deep learning. And it's the idea by which you take a signal that you want to recognize, classify, whatever, okay, observe. It could be an image, an audio signal, a piece of text, whatever. Then there is what's called a feature extractor, which is a program generally on the computer that extracts relevant features from the raw signal. And that module traditionally is built by hand, okay? So you have several ways to build such a module by hand. The stupidest way, I could say, is to just draw it randomly, and that's pretty much what the perceptron was doing. Okay, so the early experiments with the perceptron, the feature extractor was basically a bunch of binary threshold units, and the inputs were a small subset of pixels on the input. Of course, the images were very low resolution and grayscale. And there were maybe a few hundred of those or a few thousand of those units, right? So what comes out of the feature extractor is a vector of a few hundred or a few thousand numbers that represent, which motif is present or absent in the image. And on top of this, you train a McCulloch-Pitts neuron, so a binary threshold unit whose weights are going to be learned through supervised learning and gradient descent. Okay, so that's the standard model of pattern recognition. There's been a lot of different ways to build a classifier, but the linear classifier inspired by the perceptron is really the simplest one. So when the perceptron first appeared, there were articles in the New York Times that said, there's an electronic brain, and within a few years, maybe a couple decades, we'll have intelligent robots and robot scientists and things like this, right? And of course, this was enormous optimism. And it's kind of a very common thing in the history of AI that people have been overly optimistic about the capabilities of the set of methods that they just invented. Perhaps the right picture is that you're driving at 60 miles an hour, but you're in a fog, and there is a wall somewhere, but you don't see the wall, so you just keep driving at 60 miles an hour until you hit the wall. And that's kind of what happened. So there's a famous book called Perceptron, written by Marvin Minsky and Seymour Papert at MIT, that showed that if you have a linear classifier here, and if you put some constraints on what this feature extractor can do, then there are certain types of classification that those systems just cannot compute, or cannot compute efficiently at least. And that kind of killed the whole field. So what happened is then funding dried for people working on this and claiming to kind of build intelligent machines. So what did they do? Did they kill themselves? In the case of Rosenblatt, actually, that happened. He didn't commit suicide, but he fell off his sailboat and, he was never to be found. But in the case of other people working on this, they just changed the name of whatever it was that they were working on. They kept doing the same thing. They just changed the name. So they stopped pretending that those machines would eventually lead to intelligent implements. They called it things like adaptive filters, for example. Okay, so the Stanford team, for example, was working on this and said, we could use those perceptron algorithm and similar things for adaptive echo cancellation and for digital communication. In fact, my boss's boss, when I was hired at Bell Labs, a guy called Bob Luckey, invented the Luckey algorithm, named after him, and that was basically using a perceptron-like learning algorithm to automatically adjust the filter for a modem. That's what enabled digital communication through phone lines. Okay, you couldn't have that without it. And so this was not, the death of the perceptron. It just took a different name, and the ambition now was not to build intelligent machines. It was just to kind of solve engineering problems. And that's kind of also something that you see repeating in the history of AI, that whenever the ambitions of building intelligent machines dies, whatever it is that people are doing kind of changes name, but it's still there. Like, your GPS does path planning, and that used to be part of AI. Not so much anymore. I mean, it's in every AI textbook, but, it's just an algorithm. Okay, so that created a neural net winter in the sense that there was no serious researcher, or very few serious researchers, certainly not in the West, working on neural nets to build intelligent machines. From the late 60s to the mid 80s, or early 80s, I should say. Is that you, John? John Hopfield? All right, yeah, so early 80s, thanks to him. Okay, so people back in the 60s and already knew that they wanted to build neural nets with multiple layers, but just didn't know how to train them. And one question we can ask is why? Because the idea which is used in the backpropagation algorithm that we use in multilayer net is very, very natural. You just compute the gradient of some objective function with respect to all the parameters in your system, and you take a step in a negative direction. The thing is, you need to have a structure where you can compute this gradient, where the function, the input-output function, is differentiable with respect to the parameters. And if you have binary neurons, you can't do that because it's discontinuous. So basically, people were hung up on the wrong neuron, on the macular pitch binary neuron, and you can't think of backpropagation if you have binary neuron, even though it's a completely obvious idea. And in fact, the idea was used in the context of optimal control for some other purpose. So why were people hung up on binary neurons? Perhaps because they were sticking to the biology, because neurons are kind of binary in the brain. They spike or they don't spike. But perhaps also because it was the limitation of the hardware of the day. If you were to compute an electronic circuit, multiplying two voltages is really complicated. You need a complicated circuit for this. But if one of the signals is binary, it's super simple. It's basically just a resistor. If you write this on, if it's a program on a computer, you need a computer that can do fast floating point multiplication. And you just didn't have that. Even when I started school in the late 70s, computers were incredibly slow at floating point calculation. And to train, reasonably sized neural nets at reasonable speed, you need, on the order of 100 kiloflops or maybe 1 megaflop. You couldn't get that for less than a few $1 million. So, as computer scientists, we'd like to think that, or what we invent is not limited by the kind of hardware constraints of the computers we have at our disposal. But in fact, it is. Our thinking is limited by the hardware that we have at our disposal, or the tools that we have at our disposal. Our tools shape our imagination, if you want. So then there was kind of a renewal of neural nets. And John will correct me if I say something wrong, but it was largely because he wrote a paper that was extremely clear that made a connection between spin glasses, which are kind of exotic crystals, and kind of networks of interconnected neurons in a recurrent fashion, showing that maybe the minimum of the energy of a spin glass kind of correspond perhaps to memories that you recall by kind of letting your brain fall into this energy minimum. There was similar work actually that took place in Japan a few years earlier that were kind of largely ignored. But it was, a few people kind of worked on similar things. But really it's John Hoffield's paper that kind of revived the field. And the thing is that for engineers and computer scientists, neural nets were toxic. You could not mention the word neurons because your papers would be rejected. You would be viewed as a fool because of the story of the perceptron that was only 15 years earlier, but people still remembered vividly. And so what happened is that John is a biophysicist, and the physicists didn't care about the taboo from the engineers and computer scientists. And so the physicists basically revived the field. They made the field acceptable again because they didn't have the taboo. Okay, so that's kind of a mental block that stopped engineers and computer scientists from actually working on this, and they had to be rescued by physicists. In fact, one paper that really kind of fascinated me, because it was the first one that really had an algorithm that could train a neural net within units, was the Boltzmann machine model by Hinton and Senowski, just 1 year after John's paper. In fact, Terry was one of your students, right? Yeah, so there's some connection. And if you read their paper, it was published at AAAI in 1983, I think. And it's written in coded terms. So never in the paper is it mentioned that there are neurons or synapses or learning, okay? There are processing elements that are connected, and they have conditional probability coefficients on them, and they can do inference. And the title of the paper is Optimal Perceptual Inference, okay? Why? It's because if it had mentioned the word neurons or synapse, the paper would have been rejected because it would be a neural net thing, and everybody knew that the perceptron didn't work. So you had to kind of camouflage a little bit, what you're saying to get through. Okay, then in the mid-'80s, backprop just emerged. People had the idea before, but they never quite implemented it. They never had, they didn't have quite the right formulation. Those people included me, by the way. But why did it appear only then? It's because that's just around the time where you could start buying a Sun workstation that had a relatively decent floating point performance. In fact, the guys who did this, Dave Romerhard, Jeff Hinton, were working on Lisp machines. And it's the same thing. It was kind of a machine that you could have to yourself, and it had sort of decent floating point performance. And you can imagine actually running neural nets and doing multiplications. And so you didn't have to be forced to use binary neurons. So it's really the hardware capabilities that kind of let people imagine those things, which I find retrospectively very interesting. Okay, but there was clearly an inspiration from biology in all of this. And again, this was a little taboo. You couldn't say when you're, even after then, it was, serious people wouldn't say, we're kind of copying the brain, because that sounds a little presumptuous. And in fact, they're probably right. And it makes you look less serious if you claim this, first of all, but more perhaps arrogant or presumptuous. But there's a point to it, which is that you don't want to copy biology too much. You certainly don't want to copy biology just for the sake of copying biology without understanding the underlying principles. And a good example, a good case study for this is in aviation. So this is a picture of kind of an airplane from the late 19th century called Éole. It was built by a guy called Clément Ader, who was kind of a genius inventor, and he was a very good steam engine designer. So he built this bat-shaped airplane with a very efficient propeller and steam engine. And this thing sort of managed to fly for about 50 meters at about 50 centimeters altitude. Okay, maybe a couple flights. Probably destroyed itself pretty quickly. Then he got some money from the military. He was a very secretive guy, so it's kind of like Alchemist, right? And built a bigger one. This one, this is a reproduction at the Musée du Conservatoire National des Arts et Métiers in Paris. If you go to Paris, you should go to this museum. It's great. It's the technology museum. And this one possibly took off. We don't actually know because it was so secretive that it wasn't clear. There's some pictures, but it might be fake. Difficult to say. Now, what did this guy do wrong? He copied bats. He studied bats for a while, and he just copied the shape. Unlike a lot of the other people, like Otto Lilienthal's and the Wright brothers and everything, he did not build gliders. He did not build models. He did not worry about stability or controllability. He just wanted the thing to take off. And the thing took off, but was not controllable. I mean, as you can probably imagine from the shape of it. It had folding wings. It's pretty amazing. So you probably never heard of this guy, Clément Ader, unless you're French. How many French people are here? Okay, have you guys heard of Clément Ader? Okay, you have. Is anybody who's not French heard of Clément Ader? Nobody? Okay. Generally, if there are people raising their hand, it's because they are aviation buffs. So he's forgotten outside France. He left at least one legacy. Well, I mean, he invented color photography and a bunch of things like this. But he also left one legacy, which is that this guy is called l'avion. And avion is actually the word that is used to designate airplane in French, Spanish, and Portuguese. So that's real legacy. Okay, so theory is good because it makes empiricism efficient. So that's the point I made a little early on, which is that empiricism just works. You try many things and you see what sticks, and you kind of build your intuition this way and sort of refine your exploratory research that way and sort of creative juices. In fact, it's something you realize when you visit Thomas Edison's works in New Jersey, in Menlo Park, I think, same name where Facebook is, but not same coast. And he had shelves and shelves and shelves of every possible material you could get at that time. And the reason was you get an idea, you try every material to kind of try to succeed for this, and one of them is going to work, perhaps. He certainly did this with the light bulb. He tried many, many different things, and tungsten eventually worked. But the problem with empiricism is that it's slow and expensive because you have to explore many things. So theory and intuition allows us to prune our empirical search space so that we can directly kind of build something that has a chance of working. Okay, so engineering knack, as well as intuition and theory, sort of guides exploration. But exploration is a perfectly valid, if inefficient, strategy. And maybe that's where alchemy resides, okay? That's why engineering has some connection with alchemy. But theory is really crucial. It would prevent us from chasing perpetual motion, for example, right? I mean, we know we can't build perpetual motion machines, and theory tells us that. Okay, so back to deep learning. So one idea that some people had been obsessed with since the 80s was the idea that this pesky feature extractor here should also be learned. So instead of having a machine where you have to build this thing by hand and then train just a classifier, what about a machine that can learn its own feature extractor? And that's really what motivated me. That's what motivated Jeff Hinton, Terry Stanowski. I mean, a lot of people who kind of started working on multilayer neural nets. And really the inspiration for this was reading old papers from the 60s where people said, you know, it would be nice if we had a way of training multilayer networks. So how do we build a machine like this? And you know, the answer is pretty simple. Each of those machines are parameterized functions. Each of those blocks is a parameterized function, and as long as the blocks are differentiable with respect to the parameters, if their output is differentiable with respect to the parameters and with respect to the inputs, then we can train this with backpropagation. That's the idea of backpropagation. You can compute the gradient, which is a list of numbers that indicate in which direction and by how much to change each knob for every box so that the output goes in the direction you want. Okay, as simple as that. And you can do this with a procedure that costs exactly the same as actually computing the output of this network just by running signals backwards. So then there was a little bit more inspiration from biology. There was classic work in neuroscience from the late 50s, early 60s by Hubel and Wiesel. Classic work, you know, it's like Nobel Prize winning work, where they studied the visual cortex of cats and various animals and figured out that there were neurons in the visual cortex that were connected to small areas of the visual field, so basically locally connected, and that whenever there was a neuron that was detecting a particular motif in one part of the visual field, there was also another one detecting the same motif on another part of the visual field. So basically, they were kind of replicated neurons all over the visual field. So that's one type of neurons that they call simple cells. And then there was another type called complex cells. And what those were doing were integrating the response of the simple cells so that whenever, so for example, a simple cell could react to an edge, let's say a vertical edge in a particular location in the image, and then you displace that edge, another neuron is going to turn on for that edge. You displace that edge, yet another neuron turns on. So what you do now is make a complex cell that integrates the output of all those neurons, and now that complex cell is going to turn on regardless of where the edge is within this little region. So that builds a little bit of shift invariance. So now if you have a whole shape and you shift that shape, the representation of that shape after the complex cell doesn't change, or at least doesn't change much, okay? Now, so this gentleman, Kuniko Fukushima, who at the time was working at the NHK lab, which is the lab of the national TV station in Japan, said, you know, figured that he could maybe build a computer model of kind of repeated simple cells and complex cells. So that's like a retina, that's like a formation of the brain called a natural genucleate nucleus. And then you have simple cells, complex cells, simple cells, complex cells, simple cells, complex cells. Each simple cell is connected to kind of a small neighborhood on the previous layer, and you have multiple types of simple cells detecting multiple features. He did this in the late 70s, early 80s, but he didn't have backpropagation as a learning algorithm. So he designed some sort of very ad hoc, unsupervised learning algorithm that sort of worked, but it was sort of very difficult to make it work. And his model is extremely complex. There's lots and lots of knobs to turns for everything to kind of work appropriately. Only the last layer was trained in a supervised manner. Basically, it was like a perceptron. But I was really kind of inspired by this work because you know, it sort of took advantage of the structure in images and was really inspired by Huber and Wiesel's work. So that's what led me to build convolutional nets, which you can think of as a very simplified version of this that is trained with backpropagation. That's what a convolutional net is. And that's kind of a convolutional net in action. So this was, you know, in the late 80s, early 90s, there was kind of a big wave of interest in neural nets. There were a lot of people working on it and a lot of activities, but very few actually practical applications. There were a few applications that were relatively small scale, people detecting fraud for credit card and things like this. A few medical applications also that were somewhat successful. But no, like, you know, large scale application. This was probably the first one that was really large scale. We even built chips for it at Bell Labs. And in fact, the reason, so this was a group at Bell Labs called the Adaptive Systems Research Department, led by Larry Jackal. And what happened is that a few years before, Larry Jackal was promoted to department head at Bell Labs in Homedale. And is a device physicist, and he was kind of trying to figure out what to do. He went to talk to John. And John told him, well, you should build electronic neural nets. And that's what he did. And then he hired me. He hired a bunch of people, but me after a couple of years, after 2 or 3 years. And one of the projects was building chips. This is a demo of one of those character recognizers. This is me. This is the 32-year-old me, I think. That's actually my phone number in Homedale at Bell Labs. It doesn't work anymore. So I hit a key, the image has been grabbed, and then recognized. So this is running on what's called a DSP, a digital signal processor, sitting in a PC. That DSP was capable of 20 megaflops, which for the time was, unbelievable. So pretty soon we talked to a bunch of people who wanted to use this commercially in sort of ATM machines, bank check readers, the Postal Service for envelopes and things like this. The Postal Service actually never bought it. They tested it, they thought it was great, but they never actually bought it. Donnie Henderson, an engineer, and Rich Howard. I'm sure, John, you remember these people. Rich Howard was the lab director. Pretty soon we realized we could recognize multiple characters, not just one, without segmenting, which was really kind of a big advance, at least we thought. And built what we now would call structure prediction or graphical models. That's not the name they had at the time. And then put this together in a giant system to recognize checks, which by the end of the 1990s was reading about 10 to 20% of all the checks in the US. So even a commercial success. The day that we invited the whole team to a restaurant to celebrate the rollout of this system, AT&T announced that it was breaking itself up. And the whole team was disbanded. So the product group went to one of the subsidiaries called NCR. The engineering group went to Lucent Technologies, and the research group, us, went to AT&T Labs. And so basically the project stopped at its peak. So that was kind of a big success. By that time, which was 1995, 96, the whole field of machine learning had lost interest in neural nets. And I think the reasons for this need to be analyzed by people other than me, because I'm too kind of biased, perhaps. But what happened afterwards, I'd worked in various places. I did a short stint at a company in France, and then came back to Bell Labs. And we worked on the face detection system. This was very early on, like before anybody in computer vision could do face detection. We could do this with convolutional nets really fast. The second neural net winter occurred despite the fact that those systems actually worked. And we have to ask the question, why? So certainly hardware was slow for floating point calculation, as I was saying, even Sun or Silicon Graphics workstations. And so we could only train very small ConvNets by today's standard, but they were good for character recognition, perhaps also speech recognition, although they were never really superior to other techniques. Data was scarce, and neural nets were data hungry. And so there was no large data sets besides character and speech recognition. It was very, very expensive and difficult to collect data back then. And so there were only a few things, there was no internet, right? So how do you collect data when you don't have the internet? And so that limited the scope of applications of those things. If you wanted to build your deep learning software framework to train those systems, experiment with it, display, figure out debug, all that, you had to build everything from scratch. Like, there was no Python, there was no MATLAB, there was no things like that. You have to write your own programming language, basically, okay? Which is what we did. In fact, that's probably one of the reasons why we were, for a long time, the only people who could train convolutional nets, because we are the only people who spent like a year or two developing our complete deep learning environment. All of the modern deep learning frameworks that people use today are basically, descendants of this one that Léon Bethou and I wrote. And then open sourcing was not common in the pre-internet days. If you worked for a company, there was no way you could pass the lawyers to release your code. And so what happened now is that there was a whole bunch of tricks that were implemented in those, the Alchemy, the black art of neural nets were implemented in our code, but we could not release it. And then putting all of this in a long paper sort of didn't make much sense. Like who cares about all those details, implementation details? But the tools gave us superpowers. Okay, now what happened is about a year after I joined Bell Labs. So I joined Bell Labs in 1988, and about a year after, in 1989, our group hired Vladimir Vapnik, depicted here. Vladimir Vapnik was a Russian mathematician. He has close friends here in the room. And he lives not very far from here, actually. And he had developed this whole theory, which he continued when after he joined Bell Labs, that was basically a very foundational theory of learning in general, not just for machines, just learning. So in particular, we produced a bunch of those formulas that says if you train a machine on a training set, and then you have a different set, a test set, where the samples are drawn from the same distribution as the training set, then you can show that for a certain class of machine that doesn't have sort of infinite power, as you increase the number of training samples, the error on training and the error on test are going to converge towards each other. So with infinite data, the errors you get on the training set and the test set are the same. With a small amount of data, the error on the test set is going to be higher than on the training set. For a given amount of data, if you change the capacity of the machine, the size of the neural net, if you want the number of parameters or something like this, you're going to have a curve like this, which Sanjeev actually showed, where there's an optimal size for your neural net, below which you get a lot of errors, above which you also get a lot of errors, and there's sort of an optimal size where there's a gap between training and test. So this was conceptually magnificent. There was all kinds of formulas, and people tried to use this for practical things, like determining what size should I give to my neural net, or how many parameters, can I predict the generalization error on the test set that my machine will do. And that basically never worked. So it was conceptually incredibly illuminating. In practice, basically zero impact. So what people do to select a model is they do validation or cross-validation. They train on a particular set, then they measure the error on another set. And those formulas basically are completely useless for that purpose. There's been lots of attempts, lots of papers, but nobody does it in practice. And it's partly because those generalization predictions are generally widely overestimate the generalization error. And so in practice, it's much better than in theory. And then there are the problem that Sanjeev mentioned, which is that systems that we train today may have hundreds of millions of parameters. We only train them with a few million training samples. All the statistics, every textbook in statistics should tell us this cannot possibly work. It will be over-parameterized, and your error on a different set would be crazy. But it works, and it's one of the mysteries, one of the theoretical mysteries of deep learning, neural nets. But it's not because we don't understand this from a theoretical point of view that it's not true empirically. We've known that it's true empirically for decades. But somehow, people were trying to convince us that this could not be true. It was clearly true. So that led to actually a bet, because within two office separation in the same aisle, there was me and Léon Boutou and a bunch of other people working on neural nets. And then down the hall, Vladimir Vapnik, Isabelle Guillon, Cornelia Cortex, Bernard Boser working on super vector machines, kernel machines. And this was the department head, Harry Jekyll, and he made a bet with Vapnik, and the bet is as follows. Jekyll bets one fancy dinner that by March 14, 2000, people will understand quantitatively why big neural net working on large databases are not so bad. Okay? That was a mystery. Why is it that they work so well, even though the theory is not understood? Vapnik bets one fancy dinner that Jekyll is wrong. But if Vapnik figures out the bounds and condition, Vapnik still wins the bet. Okay? This was a thinly veiled incentive designed by Larry to convince Vapnik that you should work on the theory of neural nets. He never did. And so they signed. I was the witness. And this was, in 2000. But in 2000, the jury was still out. So we waited until 2005. And in 2005, it was clear that neural nets were coming back. And so, but there was no theory. So they basically both lost, or they both won. They both lost, actually. So they invited Léon and me to dinner, and they shared the check, and Léon and I just enjoyed the dinner. So after the second neural net winter, there was a spring. And the reasons for why is it that the machine learning community kind of turned away from neural nets despite the empirical evidence that they were working. And I think it's a case of mathematical hypnosis. And it's amazing to think that it actually exists, and like there could be sort of a collective delusion that something doesn't work because we don't understand it theoretically, but it is true. That's at least the best explanation I can come up with. So what you get with supervector machines and other methods that are simpler, if you want, than neural nets, is you get better theory, where you can prove stuff. You get generalization bounds, which is cute. You get convex optimization, which has provable convergence. You're not using stochastic optimization because the math is too hairy. There's all this reproducing kernel Hilbert space kind of formalism that explains what those supervector machines are doing. Very cute mathematics. You can drop names in your paper like primary dual methods, Karush-Kuhn-Tucker condition, and semi-definite programming, and that gets that impresses the reviewers. And other methods were invented around the same time, variational Bayes methods and non-parametric Bayes, and various types of graphical models and conditional random fields, blah, blah, blah. So we had backprops, we had ConvNets, we had structure prediction. The community insisted on moving towards SVM, Gaussian processes, CRF, and non-parametric Bayes. None of these methods ever beat ConvNets on standard datasets like NNIST, which is Hamilton digits, ever. But somehow there was a legend that they did. It's amazing. I had to make a web page with a big table that showed no, that's not the case. Even then. So I think, okay, I kind of pulled this off of. Okay, there was 2 years ago at NIPS, there was the rigor police, which were Ben Recht and a bunch of other people, Shai Schwartz, I think, and I can't remember who. Natis Rebo, yeah, that's right. Brilliant people, okay, and they kind of label themselves the rigor police, and it's good to have mathematical rigor, but if you have that in excess, it leads to excessive rigor. So I tried to figure out what's the phenomenon that causes people to kind of move away from empirically successful methods just because they can explain the other ones. And it's a bit like the old joke, right? That it's a streetlight effect. And Noam Chomsky, I don't agree with him when he talks about cognitive psychology and linguistics, but he has a point here. Science is a bit like the joke about the drunk who is looking under the lamppost for a key that he has lost on the other side of the street, because that's where the light is. It has no other choice. And so it's a bit of this phenomenon that I think we observe there, that people work on stuff that they can understand, as opposed to stuff that actually works, and then work towards understanding those things that actually work. So a bunch of lessons that we learned here. Hardware limitations influences research directions. Good software tools shape research and gives us superpower. Hardware performance matters. The recent revolution or emergence of deep learning actually is evidence to this. And here is something weird. When hardware is too slow, software is not readily available, or experiments are not easily reproducible because of lack of open source, people will find ways to dismiss and abandon good ideas. Okay? So I was hearing things in the late 90s, early 2000s, like, Yann LeCun can train convolutional nets, but he's the only guy in the world who can do this. Nobody else can do that. Today there's probably millions of people who can do it. So that was just not true. It was kind of a way of, kind of dismissing the fact that you had to kind of do the effort of re-implementing things. So I became a big advocate of open source after that. And despite all the cute mathematics, so here is an example of mathematical hypnosis, which is the fact that when you look at what a kernel machine or supervector machine actually does, you can write 500-page books on the mathematics behind, underlying it, which is beautiful. Which employs all the keywords that I mentioned earlier. Hilbert spaces, spaces of infinite dimensions and reproducing kernel Hilbert spaces. There's all kinds of really good mathematics you can do for those things. But in the end, what they do computationally is incredibly naive. What a supervector machine or a kernel machine does is that it takes an input vector, it compares this input vector to every training sample that you have. Basically, it's like a two-layer neural net where the first layer has as many neurons as you have training samples. And what this first layer does is that it compares the input to every training sample. Okay? And it passes through a function, a kernel function, that produces a score of some kind, a number. And then the classifier just computes a weighted sum of those things. Okay? It's a two-layer network where the first layer is not learned, or at least it's not learned supervised. It's just a copy of the training samples. Computationally, that's incredibly naive, I would say. There's a lot of functions you cannot represent efficiently this way. But when you talk to a theorist, they tell you, look, I have this theorem. I can approximate any function I want on my training set as close as I want. Why do you need anything else? It took 15 years to convince people that it actually helps to have multiple layers. Okay, I'm out of time. I will thank you very much for your attention and take questions if we have time.
So what role do you actually see for theory in the field?
Well, Sanjeev kind of hit all the right buttons there, which is we don't understand why they generalize, despite the fact that they are, way over parameterized. There's quite a bit of work on this, which is revolves around the idea that somehow the intrinsic dimension that actually matters, that learning actually works in, is much lower than the number of parameters. Most of the parameters get wasted. They don't get completely wasted because they are there to facilitate optimization. So if you have a neural net that you want to train for a particular problem, and somehow you figure out the optimal size of that neural net, just the right size so that it can just learn the training set, it's going to be very, very, very hard to train it. If you make that neural net 5, 10 times bigger than necessary, then it's much easier to train. Why? It's because in high dimension, if you have local minima or etc., you can go around mountains. You basically have degenerate dimension of the solution space, which is very high. And there's a number of papers on this, and perhaps a new resource. I was just talking to someone here from IAS. So there's quite a bit of work on sort of trying to estimate what is the dimensionality of the solution space as a function of the number of training samples, the complexity of the task, and the size of the neural net. So what we were doing wrong back in the 80s is our neural nets were too small. They were just the right size for the problem, and half the time doesn't converge. So a lot of people would try this, make a few other mistakes, and conclude that neural nets didn't work. They were just not doing it right. And they couldn't rely on open source code that they could just get from other people. So that's one question, okay, generalization. Second question is, how is it that when you what's the shape of the landscape that is such that when you make the neural nets bigger than necessary, optimization becomes easy? It's very reliable, right? I mean, you train a neural net, you always get solutions that are similar in performance. It's never the same solution because it will fall in different part of the space, but it's quite reliable. So those are like two really big questions I would think, and then there are kind of more specific questions of which are more kind of practical. How do you accelerate learning with various optimization tricks? How do you need to normalize the weights? How you train recurrent nets, which have kind of their own type of problems? I mean, there's a bunch of different things like this, but those are, I think, the two big questions.
I guess then there's things like reinforcement learning or transfer learning.
Yes, I didn't get to this because I have a whole section on reinforcement learning. But so interestingly enough, the history I told here, there is a parallel history in reinforcement learning. I think Joel will slap me if I say it wrong. Correct me in your talk if I say it wrong or just now. But there was some really interesting work in reinforcement learning in the early 90s by various people, but among others, Jerry Tesoro, who used a neural net to compute the value function, the evaluation function of a backgammon player. So this was one of the first really successful examples, non-trivial examples of using reinforcement learning to get a machine to play a complex game. And his machine actually worked really well. He beat the world champion at some point. So that was really amazing. By the time he had that success, which was about the same time that we were producing those character recognizers, the reinforcement learning community completely lost interest in neural nets also, and started working with much simpler models where the decision function or the policy is basically a table with probabilities. So there's no parameterized function, there's no neural nets. Because it's easier to study theoretically. And then they proved that, these convergence proofs when it's, you don't have those tables, you don't have those neural nets. When you only have tables, you don't have neural nets. And then it took 15 years, again, for reinforcement learning basically to decide to use neural nets again, which, happened, Joël.
I think the part where I would add a bit of nuance is your earlier comment where you said that when you run a neural net, the results you get, though it may not be the same solution, the quality of the results is essentially comparable.
That's right.
And what we saw in reinforcement learning, in fact, is you run the neural net a few times. When you reinitialize the weights, you get a lot of variability in the performance of the system. And it's that high variability that scared some people away from using neural network for reinforcement learning. Right. And in the last few years, 5 years or so, we've had much better understanding, which didn't necessarily come from theory, but we've had much better understanding of what kinds of mechanisms are necessary to stabilize that variance and give us more consistent empirical results.
Right. I mean, I think, I'm sure you're going to talk about this in your talk, and you are the expert on this, but there's a lot of stochasticity in reinforcement learning. There's the fact that the observation you're going to make at time t depends on the action you took at the previous time. So then it introduces a lot of noise and stochasticity in the system, and probably some problems that partially explain some of the problems you're observing. But for RL, which don't seem to occur for supervised learning.
So, I believe during your talk you said something along the lines of following biology too closely has not led to desired results.
Yeah.
So today's field seems to be all about bigger and bigger data sets and more processing power, however that's achieved. And I'm just wondering though, are we operating in a way that's sort of orthogonal to the way the brain works? In that, we all know we all have these 20-watt processors that don't necessarily process very quickly, and yet we also all know that we don't have to show an infant millions of training samples to tell the difference between a dog and a cat, much less more complex things. So I'm just wondering, are we going down the wrong path, or is this the only thing we can do because it's all we can really understand?
So that's my other talk, okay? So my standard talk, this is not my standard talk, this is more kind of a historical, philosophical thing, which I apologize for. But my more standard talk is exactly that point, that we're not going to build truly intelligent machines using either supervised learning or pure reinforcement learning. We're going to have to use those things as well, but they are actually a relatively minor part of overall learning, in my opinion. And the type of learning that humans and animals do is mostly, I would call it self-supervised, which means that we learn how the world works by observation, largely, also a little bit by action, but mostly by observation. Like babies are basically helpless in terms of action, but they learn an enormous amount of background knowledge about the world just by watching. We learn intuitive physics, we learn gravity, it takes about 7 months for that. We learn object permanence, we learn all kinds of stuff. Now, how do we get machines to learn this way? Just by observing, not by trying to solve a task, supervised, but by just watching videos, for example. That's the big question, that's a big challenge in AI for the next few years. And there's really promising approaches there, so things like generative adversarial networks and other types of latent variable models that basically deal with the fact that those predictions that we, one example of how you train a machine like this is you show it a few frames of a video and you ask it to predict what's going to happen next. And if you can do this relatively reliably with some decent future, that means it probably has understood what it means to that the world is three-dimensional, there are objects that can move independently of others, that they have to obey physics somehow, that there are animate objects and inanimate objects. There's a lot of stuff that the machine will have to learn if it's going to be able to make those predictions. So that approach of self-supervised learning works extremely well in natural language processing. Over the last year or two, there's been, also starting before this, it was starting with the Colbert-Weston paper from the 2009-2010, where they kind of learned word embeddings by basically just training a neural net to kind of predict other words. Then there was, word2vec, which is a very popular technique, very simple, to learn vectors associated with words in a language. So you learn to represent the language, also by using prediction. You take a bunch of words, and you train the machine to predict the word that's missing in the middle. And now there's those new techniques like BERT and transformer networks, with GPT-2, things like this, where you take a segment of text, could be 1,000 words from a corpus, and you train a giant neural net to predict words that you have taken out. You take out 15% of the words from the sentence, and you ask the neural net, predict what words were there. That works really well for text because it's easy to represent uncertainty in text. It's just a long list of numbers between 0 and 1 that's 1 to 1. We don't know how to do this with frames of a video because we don't know how to represent interesting probability distributions in high-dimensional continuous spaces. That's a challenge. But we'll find a solution eventually. The big question is, are we going to find a solution before the people funding our research get impatient?
So we have a time constraint. I know there are many interesting questions, but Yann will be here also for the panel discussion, and I hope he'll answer more questions then. So let's thank Yann. And the time constraint is that lunch is at the dining hall across the greens over there, and just follow the crowd. And we want to be back, let's say we'll run 5 minutes late, 2:05 for Joel's talk. So there's not a lot of time for all the people to go through the dining hall. So let's be efficient. Thank you.